So we did a lot of background research into what do you need to do, or what makes a CubeSat computer special, and what are the kind of things that we need to take into account. And kind of what we settled on was, number one, it needs to be reliable. Obviously, we don't want our mission to die because our computer broke, or yeah. Um, Needs to be fairly low power, because we can only generate so much from our solar panels, and we can only store so much in our batteries. Um, so it needs to be low power-ish. So for example, that ruled out something like a Raspberry Pi, which draws a couple watts when it's going, compared to this, which is like the entire system draws about half a watt when it's going. And kind of what we settled on, or what we saw, was people are either doing full-blown computers running Linux, so something similar to a Raspberry Pi, but lower power, slower, that kind of thing, but full OS, all that kind of jazz, fairly complicated. Or they were just using a microcontroller. So a microcontroller is an entire computer integrated onto one chip. Very low power. When I say power, generally I mean electrical power, but also doesn't have the computing power of something bigger. However, we looked at what our satellite needed to do. We said we're not doing any heavy processing, like we're not doing vision stuff or machine learning, or like I always say Bitcoin mining, that kind of thing. So we don't need a lot of computing power. So we're going to pick a microcontroller. Okay, so we've settled on that. Then which microcontroller do we pick? There's like the ones they use in Arduinos. There's ones meant for cars. There's ones that are very low power, electrical power. There are ones basically there's a microcontroller for like everything. So we had to do some research, and what we settled on, I won't try and find that presentation, was this line called Hercules from Texas Instruments. And so what we cared about was, number one, they have cheap dev boards. These are $30. Microcontrollers in the past, the dev boards would be like hundreds of dollars, which is not very good for getting up and running. The costs are coming down a lot recently, since people are trying to get people who have used Arduinos and stuff over using their microcontrollers by making the dev boards similar cost. And we picked the Hercules line from TI because they're industrial, like basically industrial strength microcontrollers. They have 2 computer cores on them that run at the same time and run the same code. And there's another module on there that compares the results from each core to see if they're the same. And if they're not the same, it'll like reset or throw an error or something like that. And that's really good in space. Not really. This isn't really an issue on the balloon. This is really good in space because we have radiation. So radiation can cause just random bits to get flipped inside. So let's say some bit on one of the cores got flipped, like a variable changed. This is essentially what that would cause. And it would detect a mismatch between those two, and then we would reset and fix that issue. So basically that's a very simple way to get pretty good resiliency against radiation. Other ways you can do it are have separate microcontrollers and then have a system to vote on them, that kind of thing. That's complicated, requires more power. It's complicated. It's pretty complicated. So we decided not to do that, and we decided to go with the chip with 2 cores in it, because that kind of gets us like 80% of the features-ish, while still being inexpensive, easy to develop, all that. So that's why we picked what we did. And the other thing was, I guess I mentioned the dev board thing. Cheap dev boards is very useful for us as well. So the way development started was we bought a few of these dev boards, and we looked at tutorials and stuff, and kind of figured out what we can actually do with this thing. So we'd had some experience from the balloon, and we knew that, for example, we had to schedule things periodically. So like, let's say we want to like read some sensor once per minute or something like that. That's that kind of thing we're going to need to do a lot of. And the timing requirements may change. So let's say we're reading like some temperature sensor once per minute, and then on the ground we're like, oh no, that's too much data, we don't need this. Let's cut that down to once every 5 minutes. So we need the ability to change that timing from the ground, and also the timing should be pretty reliable. And also we should be able to do a lot of things, like control the timing of a lot of different stuff. So on the satellite we have like a whole pile of sensors. We need to write that data. That's another operation we need to think about. And then also dealing with the radio. That's another big one. So yeah, a lot of things that we need to time and schedule and that kind of thing. So there are a few ways to do that. On the balloon, we did what's called cooperative scheduling. Maybe I can pull up a diagram. And the way, maybe if you're in Cubesat, you may have heard of this. There are various ways to schedule tasks. So a computer like a microcontroller can only run one function, one instruction at once. This might work. Yeah, okay. Oh, that's really small. Great. Okay, so this is cooperative scheduling. So this is what we used on the balloon. And this is what, you guys might do this, probably should. What you have is various, you can't see this, I'll move this up. Can you guys see the bottom bars-ish? Close enough. So with cooperative scheduling, you've got functions A, B, and C that need to run. So this could be reading a sensor, and the x-axis is time. So reading a sensor takes a little while. Maybe in here you've also got some processing happening on that data. Maybe you're taking a bunch of samples and averaging them or something like that. And then we've got some other function here that we need to do, like writing that data to an SD card, something like that. What is that guy? What's that doing? Anyway, what cooperative scheduling lets you do is say, I want to run this function once every certain amount of time. So I want to run function A once per minute. I want to run function B once every 5 seconds, something like that. And you can define that for each function. Hey, Tim.
So can you run the things at the same time?
No, you can't. You've only got one core. Your computer can only run one instruction at once. So think of lines in your code. It can only run one line at once. Can't do two. What you can do, and what this is getting to, is you're constantly switching between what you're actually running. So we can run function A, and then we'll finish it up. Then we'll run function B, and then we'll run function C. And when we run these is controlled by us. Well, it's controlled by the scheduler, but it's defined by us. Does that make sense? So it's constantly determining, like it's looking at the current time and saying, okay, it's been a minute since I ran function A. I need to run it again. And then A is going to finish, then it's going to look again and be like, oh, okay, need to do B, or maybe B hasn't come up yet. Maybe we can wait around. That's what these points here is. It's just waiting because it doesn't have anything to do yet based on the timing requirement we gave it. And the way it decides what to run is based on, one, the time, like the frequency you want to run the function at. So we're not going to run A here because we don't need to run A yet. That's what we've said. And the other thing is priority. So you can imagine if you want to run A once per minute and B once every 30 seconds or something, you could potentially get overlaps where you need to run A and you need to run B. So you would assign a priority to each function where, let's say it comes up, I need to run A and B because of the time, but A is higher priority than B. So I'm going to run A first, then I'm going to get to B. Does that make sense? Good, good. So cooperative scheduling, you finish each function before you get around to doing the other one, which is different from preemptive scheduling, which is at the top. So this is what we do on the satellite. And I'll get into, this is what we do on the satellite. So you can see here, we've got similar things. So we want to run a function once every certain amount of time. And after it's running a function, it's just kind of, actually, what's it doing? It's running the important point with preemptive scheduling is it will interrupt running A to check if it needs to switch to something else. So that's what it did here. So it's running A for a little bit of time. So it's like doing the first 5 lines of A or something. And then there's something else, so a semaphore. So let's say a message came in from the radio here, and that's very important. Higher priority than A. So it's going to stop running A, it's going to run thing D, and D is going to finish up, and then it's going to go back to running A and then finish with A, and then it can keep going on. So preemptive scheduling gives you the ability to interrupt what's currently running and switch to something else and then go back to what you were doing before or switch to something else. So it's based on priority as well and based on the timing requirements you give it. Does that make sense? You guys understand the difference? So with cooperative, your thing will finish and then it will decide what to do. With preemptive, your thing is running and periodically it will chop up what it's running and decide what to do. So obviously this is a lot more simple. When we were doing the cooperative scheduler for the balloon, there's actually just, this one. The cooperative scheduler for the balloon was just from this tutorial in this article here. It's like 3 parts or something. And they give you some sample code, so we took that, we changed it a little bit to make it a bit nicer for us, and then that's just what we ran. So that was a quick way to get the functionality that we needed going. So we need to schedule stuff, run things periodically, and it was pretty straightforward. We had it like up and running like in an evening kind of thing. So that's what we did for the balloon. For the satellite, as we've said, we need to do preemptive scheduling because there's a lot more things happening. We could have a radio message come in at some point. We've got a whole lot more sensors to deal with, things like that. So we need to do preemptive. So, okay, how are we going to do that? What we settled on is this, which is called free RTOS. So RTOS stands for real-time operating system. So an RTOS is just, free RTOS is a preemptive scheduler. And then they give us a bunch of features for other things that we need, which we may get into. So the reason we picked free RTOS was because they already had a version of it for this chip. And in the configuration software for the dev board, there's examples of how to use it. There are YouTube tutorials on how to use it. It's supported, so it's like pretty easy to get going. It's kind of like plug and play. So we decided to go with free RTOS. There are a bunch of others. There's like there's one called Zephyr. There's one called VxWorks, which is an industrial one. Intel owns it now, but that's what they use on the Mars rovers is VxWorks, and it's an RTOS as well. It's just a commercial one. Other thing is spacecraft tend to use RTOSs, so we should probably use one too. People smarter than I am have thought of this. Yeah, Tim.
What does RTOS stand for?
Real-time operating system. You weren't listening, were you? I mentioned that already. Anyway. No, feel free to ask questions. I'm not gonna.
Different rating systems. Better than Windows, let's say.
Okay, so So the distinction, the real-time part, basically mean click. Okay. The real-time part versus like a desktop OS like Windows or something, Windows, Linux, OS 10, is that a real-time operating system deals with information roughly as fast as it comes in. So you can think about like on your computer, you can have big delays between when data comes in and when it's actually dealt with, just because it's running so much other stuff at the same time. A real-time operating system is lightweight. It's designed to deal with data as it comes in. So as something happens, switch over to this task and do it. Versus your desktop operating system, which does some of this depending on what is actually happening, but is a lot heavier weight and not real time. So you can think of like trying to open an application and then like waiting around for it to figure its stuff out before anything actually happens. Does that make sense? Yeah. There are like some other differences that I can't really explain. You can Google it if you like. But basically an RTOS is fast-ish, deals with information as it comes in, lightweight, easy to use, that kind of thing.
I think the reason people use it is because you have control over how things are executed, especially on the scheduling level versus any other operating system.
Yeah, that's a good point.
What you want to do here, you want to have control over how things are executed. So when the radio message comes in, you want to make sure that you are listening and saving and processing when it's needed versus like usual operating system, which is does a lot of things for you, but you have less control over what it does.
Yeah, that's a good way to explain it. Yeah, so we have very good control using an RTOS when things are going to happen. We can say run this function once every 2 seconds, and for the most part, unless something goes wrong, it's going to run that every 2 seconds, unless there's like some higher priority going on. So that's all good?
I have a question.
Yeah.
Just kind of not related, but
no, it's fine.
Does Team Guardian use RTOS?
Yeah. So the flight control software is called APM. Were you at the workshop on Saturday?
No.
Okay. APM Auto. Okay. So Team Guardian runs a software stack called APM. And APM is a whole bunch of things at once. So at kind of the base-ish level, they use an RTOS to manage everything that's going on. And the things that RTOS is running are functions to read the sensor data in, functions to do all the calculations for, like, imagine a quadcopter, do all the calculations for how fast to spin each motor to go in a certain direction. Doing state estimation. So they need an RTOS because they have a lot of things that need to happen pretty quickly. They need to be always updating their sensor data so that like they know where they are and how fast they're going and stuff. They need to be doing a bunch of math to figure out how to actually fly. And they need to be checking for failures and stuff like that. So that's when you use an RTOS, when you have a lot of things that need to happen and you have fairly strict timing requirements on them.
And just in general, it's not just in Guardian, it's an industry standard to use RTOS on any sort of like real-time critical applications like cars, probably run some sort of real-time operating system on their microcontrollers, planes, drones, and everything else.
Yeah.
A lot of medical equipment as well.
Medical equipment, yeah, anything that needs to respond quickly. So Mars rovers run VxWorks. A whole pile of satellites and space probes run VxWorks. What else would run it?
Skytrain?
Skytrain, maybe. Yeah, if they're running anything, it's probably going to be VxWorks because this is the industry standard for real-time operating systems, but it's expensive and stuff. Actually, hey, there's a Skytrain type of thing. So, buildings? No. Planes? Yeah, maybe. What the hell's that? Oh, robot arm.
I heard that Linux is really good for real-time stuff.
Depends. You can run, depends how much extra stuff you're running on top. So like Linux, at the core, there is just a scheduler figuring out when to run each function or task. Yeah, you could use Linux for real time. Yeah, but we don't have the processing power for that on the satellite.
And there's something like real-time Linux as well. I'm not sure.
Yeah, that's what I was thinking of. Yeah. Like at the core, any operating system has a scheduler. With the real-time operating system we're using, we just pretty much need the scheduler and then some other stuff around it to bring data in and out and that kind of thing. Yeah.
Also, just a suggestion, I think a lot of people are taking CPT 127.
We're about to look at some code, yeah.
So I don't know if you can sort of like make parallels between what you're
yeah, I hope I can.
Or their course that is
yeah. Trying to think. We didn't talk about this stuff in my computing class.
You know how how this relates to what kind of assignment that you're working on right now.
Had to reverse a string yet? Not yet. Oh man. Okay. While loops. Okay.
Pointers. Oh yeah.
Okay. Yeah, they're
While loop is, I guess,
there's a shit ton of pointers in this kind of thing, so we'll get there. Okay.
Like in a while loop, you have things like using sort of like one after each other. But what Richard said, if you want to kind of like execute things based on some external input like radio signal, you can have just the while loop. So I guess you have some sort of while loop, but it will be interrupted as other things come in.
Yeah. And actually, you'll see each task in the RTOS is an infinite loop, which seems weird, but it just has to do. I don't really understand it. They just do that because of internal reasons that I don't know. Yeah. So like, this is. I wasn't gonna get into this yet, but we can just look really quickly. So this is a task. So a function we want the RTOS to run, and this is just turning a pin on, suspending this task for a while so the scheduler can then go do other stuff, determine if task B needs to run or something like that. Then it's turning this pin off, and then it's doing that again. And then since it's a for this I call this a forever loop, same as a while one loop. So then we'll go do this next time this gets called.
Wait, what libraries are those at the top?
These, that's actually a good segue. Thanks for asking that. Yeah, so you won't see these in your computing class, but these, okay, yeah. This guy, this is very important. Does anyone know, well, who has used Arduino? A couple people, yeah, okay. So you know the digital write function? Probably used it. So digital write, so on your microcontroller, there are pins, right? And those are those are your interface to the microcontroller. So you can turn them on and off. So they'd be an output, or you can make them an input and connect them up to like a button, and then read whether that button's pushed or not. So in Arduino, the digital write and digital read functions are what do that. In our code, it just does the same thing, but it's called a different name. GIO, general purpose, input, output, set bit. So this is using it as an output. And then these two things just tell us which specific pin on the chip we want to toggle. And then one is just saying set it high. So turn that pin on. And this pin is actually connected to an LED on this board. So when we run this, it'll blink. Because we're turning it on, we're waiting. So it's going to stay on. And then we're turning it off. So it's going to stay off for 300 milliseconds and then turn back on again. Does that make sense? Okay. So yeah, microcontrollers have pins on them. So we have general purpose, well, GIOs or GPIOs, which let you read or write to a pin. So just give me a sec. So in Arduino, you can say it's like what GIO 1 to or 0 to 13 generally and stuff. So those are just mapped to specific pins on their microcontroller. On this one, why am I not looking at my screen? I don't need to break my neck. On here, where am I going? Examples. So, yeah, actually here, I'll, oh yeah, it does that. There we go. Actually, I'll show you guys something that'll scare you a little bit. Actually, no. So, when you're working with chip, your Bible is the data sheet. And this shows you how to use everything on that chip. And let's just see how many pages this guy is. That's always fun. Oh, these Atmel doesn't have an index. Let's go to the end. So, shit. Oh, they do have an index. It's at the end? Why did they do that? So this data sheet is like 650 pages, and this describes how to set up everything that this chip can do. So if we look, yeah, I always thought they didn't have indexes. They're just at the end. That's really dumb. Anyway, so this is describing how to use everything. So let's say there's going to be a GPIO section, SPI, UART. Loader, memory, electrical. Maybe I missed it. Should be. It's taking a while to search this huge thing. So this data sheet, this is for the microcontroller that is the heart of the Arduino. Oh, here we go. Yeah, perfect. This data sheet is 650 pages. For the one that we use for the satellite, there's a data sheet which is like 1,200, and there's a technical reference manual which is like another 1,000 or something. So these are very complicated to figure out from scratch how to do anything. So this is describing, oh, here's some more code. What's that doing? Assembly. Ooh, assembly. This is describing how, that's just a, is there no GPIO section? Anyway, this is not the best example, clearly. It helps if you plan things. This describes how to set up everything the chip can do. Obviously, reading these diagrams and going through all this stuff, all 650 pages, is horrible and is not very fun. That is what Arduino has done for you, and has just wrapped all of that in functions like digital write. So we can just say digital write pin 13 high, and then it'll go do it. And it's using the information from the data sheet, it's figuring out the instructions to send behind the scenes. So that's fine. On Arduino, it's already done for us, and it's already configured which pins are inputs, or which pins are GPIOs, which pins do, and which pins do other stuff. For this, there is no Arduino, so we need to configure all that stuff, and that's what this software is used to do. So most microcontrollers will have a similar thing, and so, for example, we can go to the GPIO section, and we can say this one, so port A0, which corresponds to a specific pin on the chip. We can say, I want that to, oh, it's this one. I want that to be an output by clicking this box here. And then what we do is we do file, generate code. I won't do it, as I don't really need to right now. And then it will generate essentially all of the Arduino backend stuff. So, well, a similar thing to all the Arduino backend stuff for us to set all of that up. And a microcontroller like this one, as they get more complicated, they get a lot more configurable. So we can do, like, well, all kinds of stuff with this. And set it up graphically, generate the code, and then we can start using it. So for example, Halcogen, which is what I just showed you, generates like the drivers to tell the chip specifically how to set itself up and gives us functions for how to use the various features. So Blinky V9. So in here, when we include GIO.h, this is what Halcogen has generated, the drivers for the GPIO pins. Do you guys know what header files do? Hands up. Okay, some of you? Okay. I guess you probably touched on them in class. Okay, good. Yeah. So we can look at the header file. So you can see Halcogen has created headers for like every feature of the chip so that we have access to it via software. So here, what it's doing here is like, well, it's creating some macros to set stuff up. So you can see, there should be a 1 in here, never mind. These are the functions we have to work with. So we can set direction. So this will set an input versus an output. We can also do it graphically, at least to start, but maybe we'll want to set it up graphically, or we want to make it an output initially, and then we may want to change that to an input in our software, so we can do that. We can set, so that is using it as an output, turning it on or off. We can get the value, so using it as an input, determining if it's high or low, whether a button's pushed or not, for example. So all of this is generated for us, which is very nice, because if we go into the file for where these functions actually are, this is doing all the datasheet setup stuff. Will you want to write this? I don't want to write that. That looks horrible. Like, this isn't even a bad one. And that looks gross still. And it's very abstract and hard to see what's actually going on. So turning this into toggle bit is a hell of a lot easier. So it's good that we have that. Anyway, so now that we have access to our hardware using these set of functions, we, can start using it like we do here. Yeah, so I already explained what that did. So the gist of it is, this software, Halcogen, lets us set everything up, and that's very good because setting it up manually is horrible. And they give us just the baseline functionality that we need to start with development. So that's great. Now we should actually do something with it. So let's walk through this code. Actually, I'll just add some lines under here. Bring that up for you guys. So think of this, well, this is your main function. So this is what gets run when we start up. So the first thing we do is we initialize our GPIOs. So what this will do is set them to inputs or outputs based on what we told it to in Halcogen down here. Okay, good. Then we're getting into RTOS territory again. So we're going to create a task, and the syntax here doesn't really matter, but we're going to create a task, and it's going to use the function. I'll just hover over it. There it is. The function called vtask1 is what this task is going to run. So here, which is just up there, is where we've defined what this task is actually doing. So it's running this stuff. And then this is just a name for us for like easily seeing what's going on. And then this stuff doesn't matter. This one is the priority, which is good. And then the rest of it doesn't matter. And then if this, yeah, that's fine. So we create this task. So we're letting the RTOS know that we have this as a task and we want to run it. Is that good? Pretty straightforward. Then we start the scheduler. So we start the RTOS going, and then it starts to do its thing. And, well, this is all that's going on in this example, is it's just running this over and over again. I can show you what that looks like. So this is how we develop, where we'll write the software and then upload it to the dev board. Hopefully this works. I haven't done this for a while. So save it, sure. So what we're doing is we're connecting up to the board. This is the same as you do in Arduino, it just looks a bit different. Oh, shit. Great, eh? Real good example, Richard, I trust you. Sometimes it has issues connecting. Oh, am I doing anything weird with this? I have all these wires because I was trying to debug something. Do you guys know what do you know what an oscilloscope is? Hands up. Okay, good. What I was doing, the reason I have all these wires connected was I was using a logic analyzer, which does the same thing as an oscilloscope. It's a good picture. So this is time, but these are the signals. So an oscilloscope is going to show you analog, so it's going to show you the entire waveform. So it could be like a sine wave or something, any voltage in between some level. For digital stuff, we know it's either just going to be high or low, like 3.3 volts or 5 or 0. So we don't need a full-blown oscilloscope to look at those signals. So a logic analyzer just tells you whether your signal is high or low. So this is high, oops, this is low. We've got a bunch of different signals connected. And this is just showing you over time on X what they look like. So for example, the blinking LED would just be high for a while, it would go low, or low for a while, go high, and just alternate like that, kind of like this. So yeah, I was connecting it up to a logic analyzer to see what was going on. So let's try and get this to actually work. Oh, I know why, I think. Maybe. Yep. Yeah, I was messing around with stuff, so I changed something that... There we go. Okay. So what it's doing is it's compiling that code, and then in a second you'll see it's going to load it onto the board. There we go. And so it's erasing everything that's on the board right now, and then it'll load it on. It's not the fastest thing in the world. Good. Okay. So it's loaded up, and look up. You're probably not really gonna be able to see this. Look up at the top here. If everything's working. Did I set a breakpoint? Shit. It's not working. What did I do? Let's check the code. I'm just gonna do this old way. That's weird. A2, is that right?
Can I interject here for a moment?
Yep, sure.
On Slack, I posted about the engineering competition. Did everyone see that? No? Yeah. So there's an engineering competition happening in a few weeks, and it's a super exciting thing to get involved with. And there is a category for first-year students called Junior Design. And the way it works, you make a team of 4 people, either 4 Burnaby students or 4 Surrey students. And you join the competition. It's on one of the Sundays, I think Sunday the 29th. And you compete against other first and secondary students. It's a good experience. It's a lot of fun. And if you win, you get to go to the Western Engineering competition, which is a big deal. So I strongly encourage you guys to form with teams and join the competition.
Yeah, it's really fun. You'll have a good time. Junior design is interesting. Yeah, they'll give you like a task and a bunch of materials which you have to buy with like fake money. So you have to optimize for cost and then still make whatever thing happen.
Is anyone interested in that?
What time is it? Do you know?
It's Sunday 9 till 3 or 9 to 5,
Yeah.
something. like a day long run.
What's the date?
When's in there?
Oh, that's when I was gonna do the board assembly. Nobody go, come assemble boards. No, just kidding. You should go to it.
Have an outreach event on the same day.
Oh, jeez. Okay.
But maybe just talk to your neighbors and after the meeting and form a team or talk to your friends. And yeah, just sign up.
Okay, so I have it working now. So this LED at the top is blinking. So that's good. So it's simple, but think about we've actually done a lot of stuff in this example, right? So I didn't actually do it, but if I was starting from scratch, I would have configured the chip to use the certain pin as an output, and then generate the drivers for that. And then we got the RTOS going, and then we now know that it's successfully running this task and that everything's working. So like when you're doing embedded systems like this, typically you always have an LED that should be blinking because it's a very easy way to see whether everything is screwed up or not. Because if your LED is not blinking, then nothing more complicated than that is going to work, that's for sure. So like on the satellite, well, we'll probably turn it off for power reasons, but anyway, we should have it. We do during development for sure. So does that kind of give you guys a bit of an overview about RTOSs and microcontrollers and stuff? Okay. What we can do next is, what was it called? Just gotta look around for something. Actually, we can do. We'll look at the official satellite code. So this is what is on GitHub. Well, all of the Blinky one is on GitHub and stuff too. We'll look at the satellite code and kind of walk through that, some of that. Where am I going? Source, main. So you can see for the satellite, we're including a heck of a lot more stuff because we're doing a lot more things. We have the RTOS stuff. We have ADC, that's analog to digital converter. That is analog read in Arduino speak. We have GIO. We have SPI. So SPI is a communications protocol. Stands for Serial Peripheral Interface. So imagine it's like a USB port for a microcontroller, and it lets you connect up to something else. So, for example, SPI, we talk to the real-time clock on the OBC, and we talk to these 3 external memory chips. So it's like having a USB connection. It's just slightly different technology. SPI is a little bit slower than USB, but it's a lot more straightforward. And like your Arduino has SPI. I think, what do they call it? Call it wire? No, I think they call it SPI in Arduino as well. Where's a good example of one? Okay. Oh, these are so small. That'll do. So like the way SPI works is we have a clock down here. So this is just constantly going up and down at some rate to keep everything synchronized. And then we have MOSI and MISO. And this is not soup, unfortunately. Hilarious. I've always thought of that joke. I've never had it. It's not even a joke. I'm a joke. Anyway, now they laugh. So we have MOSI and MISO. So this stands for master out, slave in, and master in, slave out. So generally your master is going to be your computer. So the OBC, the Launchpad dev board, the Arduino, whatever. It is the master. It is controlling everything. So it has a line for master out, so sending data out of the microcontroller, and it has a line for master in, slave out. So the slave, so your sensor or whatever you're connecting to, sending data in to the microcontroller. And you'll see it's all synchronized with the clock here, right? So this guy's ticking up and down. And so it ticks up, and then this is going high for, 1, 2, 3 clock cycles. And then it's going low, and this is all synchronized. So the clock will go high, and then some data will start happening, or stay happening. And what your microcontroller or your device is doing is every time the clock transitions from high to low, low to high, actually it can be both. They're different standards. Let's call it low to high. What it will do is it will either send out, so after a short delay, it will send out or change its pin to go high or low, or it will read what the input pin is doing. And that lets you transfer data. So we can say like imagine binary, right? So 1, and say we're sending 8 bits, and we want to send out a 1. So over that 8 bits, our clock is going to go up and down 8 times, and we're going to be 0 for all of it, except we're going to be high for 1. So 1 bit is going to be set to 1, and that means 1. Does that kind of make sense? Yeah-ish. Any questions about SPI or that kind of thing? Okay. Yeah, so this is how your microcontroller talks to stuff, by sending data out as pulses that are synchronized on with a clock and getting data in. And there's, so we have, what was I looking at the code? So we're including that. PMU, won't get into that. So we're including the Halcogen one. So it's called MIVSPI in this case. And then we have an SFU one. So what we've done is we've wrapped everything to make it even easier to use for us, and like configured stuff exactly how we want it. So I forget what's in here, but we can look real quick. Wow, nothing. Or not much. This is just configuring it to do exactly what we need it to do. We won't get into that. That looks gross. I didn't even write that. I don't know what it does. Okay, we'll keep walking through. Skip that. So then we get into main. Okay. Enable interrupts. Let's not skip that. We do GIO init again because we want to blink that LED. Then we initialize serial. So there are various communication protocols. So there's SPI. There's I2C, which is does the same thing, but doesn't have an input and an output line. It uses one line for data going in and out. And it just has to synchronize, so there's only data going one direction at a time. There's I2C, and then there's UART, which is different from both of those. But it does the same thing. Lets us transfer data around. And the UART is how in your Arduino, when you do serial read or serial write, so like send text to and from your Arduino, that's over a UART. And so we have one of those on here as well, and that's how we communicate with it. Let's skip that. So we initialize our SPI for our various things that need it. We initialize our ADC. We do that. RTC, so we initialize our real-time clock. Interrupts again. We don't need to do that again. It's fine. Oh, this is the Triumph. This is what I wanted to look at. Okay, good. Actually, let me... RTC. So I'm going to upload this. It might not work. Because again, bear with me. Same issue as last time. So this code was changed or had some features added for the testing at Triumph, the radiation testing. So there are a couple hacky things I had to do to get everything working, but we don't need to get into them. But anyway, the extra hardware that we were testing in the radiation isn't connected. So for example, if it's trying to read that hardware and gets nothing back, it might die. So I don't know, I haven't done this. We'll see. if it works, it'll be kind of useful. We'll be able to see various things happening at once. That's going, and I gotta do that. Let's do that. So this is in Arduino, when you connect to the serial monitor, this is that. And still loading, okay. So we'll see some stuff here, and then it might die, I don't know, hopefully not. There we go. Yeah, oh, that died, okay, of course. Okay. So we'll look at where this came from. But it sent out some data for us, right? So this, actually, that's not important. Let's just look at some of the tasks that we're doing. So think satellite stuff, right? We do a blinky, so this is blinking LED just as we had before. Then so for the Triumph testing, we have our flash memory, so our external memory, and this like isn't going to make a lot of sense, right? And I'm not going to go through all this because that would take forever. But what we're doing is we have a task that will read from our external memory. Actually, we use the version 2, I think. And we also have one to write to our external memory. And the thing it's writing, this actually says SFUSat. So this is S in ASCII is 83, so on. I call it thing. Great. You guys are seeing excellent code here. This is not good at all. Anyway, what we're doing is we're writing the word SFUSat, and then we're also writing the time from the real-time clock, into our memory. And we're basically adding, and then we're delaying 1 second. So task delay, delaying 1 second, and then we're going to come and do that again. So this task will run once per second, kind of like the blinky, and it will write into our memory, and somewhere it will write, it'll append to itself every time. So think of like a text file, and we're just constantly adding to the bottom of that SFUSat and then the current time. So it's simple, right? There are only a couple different things going on, like hardware-wise, but it's a pretty good test because we are working with the real-time clock. We're writing to our external memory. We're making sure that the RTOS is working. And then we're also, at the same rate, we are reading from our memory as well. So we can check that what we thought was written in there, so SFUSat and then like some number of seconds, was actually written into the memory correctly, and then we can read it back correctly. So for example, if something got screwed up because of radiation, we would expect to see SFUSat 1, SFUSat 2, SFUSat 3, because it was writing it once per second and incrementing each time. But if we saw SFUSat 1, SFUSat 0, 0, 0, 0, 0 or something, then we've had some radiation event that messed things up. So that is how we test for that kind of thing. And when we read it, we send the data out over UART, and actually, flash, Triumph data. That's what we want. Yeah. And so this is what we're reading, yeah. So this is just waiting for it to connect up, pass test, start state machine, all that kind of stuff. You saw this down in the bottom right corner of the screen when we start up. So this is the system starting up, and just some other stuff. And then we get into things, SFUSat 4, 5, 6, and these other things are running as well and printing back information for us.
So for the Triumph test, you were firing radiation at the chip?
Yep.
And then did it succeed?
It did, yeah. So, for example, UV, so there's an arbitrary unit that they were using for amount of radiation that the chip was receiving. And UVic had kind of a standard microcontroller. They lasted 6,000, and then their thing died. We lasted 350,000, and we were still going. So that, yeah, that's right. Get fucked, UVic. So that kind of goes to show how, that this system is fairly reliable. I'm not going to try and find it.
So after 350 seconds, the chip just failed altogether?
No, that was just the
350,000
units.
units.
That was just the end of our test. We kind of ran out of time.
Oh, so you just beat the whole...
Yeah, so we were fine. And that was simulating, they were saying, about a year and a half in space in terms of radiation received. So that showed us, anyway, or at least, like, according to that test, we should be good for about a year and a half, at least. But, I mean, radiation's random, right? So you could get, like, some crazy particle on, like,
Solar
on the first 5 minutes that totally blows everything to shit, but hopefully not.
So shitty.
That would suck. Yeah. But anyway, it shows that it's fairly resilient. It did actually, I don't know if I can find it.
Is it correct?
It did, yeah.
Does it reset the numbers, or?
No, so that kept counting. It just printed out some weird stuff for a couple times. Actually, I have it in the spreadsheet. And then, so it's either an issue with the code. I haven't checked yet. I'm pretty sure it's not. Because essentially this test was running for longer than I ever got to test the actual code beforehand. So it could have been like some issue with the code I wrote, but I don't think so. Consolidated, yeah. So you can see 1505, 1506. Okay, that's fine. And then what is that? What? Right. So it did a couple weird things, and then it seems to, and then this is consolidated, so I cut out some stuff in the middle. But it goes weird, and then it fixes itself.
That's so cool.
So it's either a code issue, which probably not, because everything else worked fine. There's really no reason for it to do this, other than some radiation thing. So that's kind of cool.
Did any other teams test anything standard like Raspberry Pis or Arduino or something like that?
That's a good question. Yeah. So Larry, the CSDC guy, has told us that last time someone put a Raspberry Pi in the radiation, and it lasted like a couple minutes and then just totally died. Yeah, so it's kind of a reason we use a chip like this.
Also, I think last time some teams wanted to use like a smartphone.
Oh yeah.
Do you know how about that?
I'm not sure. Yeah, I don't remember everything he said. But so essentially, like, as chips get more advanced, you may have heard that like the feature size of the chip, so the size of every transistor gets smaller and smaller. So right now they're at like 14 nanometers or something, which is like a desktop processor. So very small devices, and so they can put more of them onto a chip. And as they get smaller, they get a lot more just general issues with trying to keep the thing stable. So as they get kind of closer and closer to that line of like, we can't actually physically make this work, radiation effects get more pronounced. So it becomes easier to trigger some kind of bad event or some kind of upset as technology is progressing. Because they're making the chip size or the feature size smaller at a greater rate than they can improve the reliability of stuff. Yeah.
Is it beneficial for us to like coat the computing like unit in like some sort of like foam or something
That's a good question.
I'm pretty sure that they do that like
Mm-hmm.
out in actual radiation.
Yeah, it's a good question. There are a bunch of types of radiation that are all flying around in space, and the energies that they happen, or the energies that they are at, some of them you can essentially, shielding is useless. They're so energetic that they'll go through like 2 inches of lead, no problem. So obviously you can't shield against that unless you have like a huge weight budget and stuff like that. They're also not very frequent, so you don't really need to. You're probably going to be okay. Other types of radiation, and this all depends on your orbit and the time of year from the sun and that kind of stuff. Other types of radiation, it can be beneficial. I believe the gist of it is where we're going to be orbiting, we don't really need to worry, and it's impractical to shield against anything. But I mean, like, you're sort of, it's kind of up to nature whether it's going to throw a crazy energetic particle your way. But we can simulate the effect of being out in space, getting exposed to that lower energy radiation over the course of a long period of time. And that's what we did in the test. What else? That's some more tasks. Yeah, that's about it, I think. Does that kind of give you guys an idea of kind of how everything works, how the RTOS can schedule stuff, and like how pins work, GPIOs and things like that? Is that somewhat helpful? Yeah. Yeah, and that's like the overview of the testing at Triumph. So the idea was to kind of run essentially everything we're going to normally be doing on the satellite. So logging data, reading data, scheduling stuff, run all of that functionality just in a straightforward way, since didn't have much time to get the code working. But it's kind of a good overview test of how the system should function. There was another, oh yeah, just one last thing I'll touch on. Where is that? Yeah. I'll bring this up as well. One important thing in reliable systems is the idea of a watchdog. So a watchdog is separate hardware from your computer that will reset you if you don't send a signal to it over a certain amount of time. So imagine, well, there are kind of two cases that we're covering here. So we have the external watchdog chip on the board, and we need to send it a signal, say, once every second, or else it's going to reset the entire computer. And that covers something like a coding issue where we've ended up doing an infinite loop somehow. Because if we're doing an infinite loop, we can't get to the code that will communicate with the watchdog and tell it that we're okay, because we're looping forever doing something else that's wrong. Or potentially radiation could cause some internal issue that would prevent us from triggering the watchdog as well. So the idea is if we don't communicate with it for, say, a second, it will reset us entirely. So that's what we're doing here. We call it tickling the dog. That's generally what they call it. And this is essentially the same as Blinky, right? So we're setting it high. We're waiting 1 millisecond because it needs to be high just for a little bit of time for the watchdog to notice that. And then we're setting it low, and then we can wait half a second before we go do this again. So this is another task that's running, and during the radiation test, we had the watchdog connected. So if radiation or some coding issue meant that we weren't able ever to run this task, then the watchdog would reset the chip because it hadn't been talked to. Does that make sense? And sort of the way this works into some other stuff is the chip, I won't go find it, but it has some self-testing code that it runs before it even gets to main. So it runs like very first, right when it starts up. And the self-testing code is built, or the self-testing hardware is built into the chip. And that's another advantage of the chip we chose. Usually you don't get that. So what it'll do is it'll self-test some various part of the chip. Internally, we don't need to be concerned about how that works at all. But if a self-test failed, what we do is we just wait forever. So it's like if self-test failed while 1, so just loop, then we won't ever get to kick the watchdog. So then the watchdog would reset us. And then hopefully that hard reset would fix whatever issue caused the self-test to fail. So that's another reliability thing that we're going to do on the satellite and that we did during the radiation test to make sure that if the self-tests fail, we would always reset. Does that make sense? Yeah, so it's just kind of, this is what like systems engineering is about. Taking a look at your features and what you're able to do and figuring out how to connect it all up so it is useful to you. So like, we knew we had the watchdog, we knew we had the self-tests. Okay, how can I get my watchdog to trigger when a self-test fails? Okay, I'll loop forever and then I won't ever get to kick it or tickle it. That's kind of systems thinking in a nutshell, at least in the context of computing. So that's the kind of thing we need to do on the computing team, and that's the kind of thing we'll work on. Yeah, that's about all I have to say for this. Hope it was informative. Thank you. Does anybody have any questions about computing, microcontrollers, all that kind of stuff? No? Okay, I gotta go now too. So. Thanks for coming. Research balloon ideas. Yeah, it only works for the Hercules line.